Okay. Cell potentials. What the little voltmeter reads on these electrochemical cells. It's another word for cell potentials. But Hagar the Horrible, I don't remember reading these cartoons, but they still have Hagar the Horrible, I think. Right? But one way to stop an army, pretty much any army, I think, even to this day, is rust. Right? And rust is a electrochemical process. And how do you stop rust, right? Like how do you stop this from happening? Well, the answer are these little guys. And we'll dig into that more the next class period, but they're called sacrificial anodes. They'll essentially rust before the iron will. And like I said, we'll talk more about that in detail later. And these little diagrams and pictures are just the two half reactions for rust occurring. So with this electrochemistry and cell potential talk, I think it's kind of, electrochemistry has been around for a while. It's extremely useful. But since it's been around for a while, you end up with a lot of terms all for the same thing. So in the homework, when they refer to cell voltage, cell potential, EMF, E-cell, they're all the exact same thing. It's what's read on the voltmeter. So what's the voltmeter? Well, here's a battery, right? What volt are these rectangular batteries? Not 8. 9 volt. They're 9 volt batteries, right? So if I want to see if it's dead or not, you use a voltmeter. So you hook up the voltmeter. So black goes to negative, right? Red goes to positive, right? Okay. Turn on the little voltmeter, set it to volts, and it reads. So is it bigger than 9? Yeah. Is that typical for these batteries? You read, because no one wants to buy a battery that's going to die in a year. They want Duracell. Ooh, 3 years, 5 years. Well, yeah, they're good batteries, but they also bump it up more than 9 volts. So then it doesn't reach 9 if you just leave it in the package, right? It lasts longer. What would happen? Let's go back to 9 volts here. What would happen? All right, you got the 9 volts. What would happen if I switched the little probes around, made plus to minus and minus to plus? What would happen? Vivian, what would happen? Man, should I be holding this thing? It's no big deal. Nobody knows? I guess you got to take general physics to play around with this stuff. But these things are so cheap. You can play around with these guys, right? At Walmart will sell. Don't go to Walmart. Target. Go to Target. $5 and get a cheap voltmeter. Not a nice fancy one like this, but it'll work. What does it read? Just change sign. Just change sign is all. Negative. So this is the only reason why they said, oh, you better make, when you make these little cells, no matter where you are in Europe, Australia, the United States, you always want the anode on the left-hand side, right? So everyone reads the same sign all the time. No one, some people don't read plus, other people read minus. Everyone reads the exact same. So everyone's connecting things the same way. Okay. That should all, yeah. Maximum electrical work. Maximum electrical work. Here's the homework, a good chunk of it. Find the maximum electrical work when 45 grams of silver is produced in a Voltaic cell with EMF of 1.15 volts. Sounds like a really expensive cell if they're using silver, but that's just how it is, I guess. Okay, and then they gave us an overall reaction. And then it's easiest to calculate this maximum work just using this equation. Now it's work So we should end up in what units? Vivian, what units should we end up in for work? What units are work? It's a hard question if you haven't had physics, I guess. Work is what? Work is the same as energy. It's just transforming energy from one form to another. So it must have units of joules. Work is joules. So we better end up in joules for work. Okay? So that F is just going to be a constant. Crystal Munoz, what is that F going to be? It was called whose constant? Starts with an F? Faraday's constant. Right? And I gave you this stuff, but I don't know. Anyone remember reading what it was in the book? 96,485. What it is if you take 1 mole of electrons, what's the charge? It's 96,485. What is the unit for charge? Coulombs. Big C. Coulombs. So there's 96,485 coulombs in 1 mole of electrons. So that's just the Faraday's constant. It's the charge in 1 mole of electrons. In this question, what would E cell be? That 1.15 volts, exactly. Okay. So all we got to do is figure out what that little n is. Because if we give you F, E cell is whatever the voltmeter reads, so it seems like they have to give you that. How do you get little n? Hint, n is the number of moles of, Ellison, what would you guess? Now, the hint would be you're multiplying n by F. And look what F is. Electrons. So the answer would be moles of electrons. Okay, so somehow you got to figure out the moles of electrons that occurred, right? You use this battery, hook it up to a little car, it drives around the room 10 times, right? How many moles of electrons were sucked out of this battery? That's literally what n is, the number of moles of electrons. Okay. How do you get it? It can be found using an appropriate half reaction. Okay. So n is just moles of electrons. One last little idea here. I don't know if it helps. But we said work had what units? Joules. Well, it looks like a what times a what is a joule. Faraday is in coulombs, because the moles of electrons cancels out. E cell is in volts. A coulomb times a volt is a joule. So I guess you could give your units for work as CV or joules. Joules is going to be better, though. It makes a little more obvious. Solve the above problem. Okay, we got to solve it. So fine. W max is minus N F E cell. We know what F is. We know what E cell is. You got to figure out the N. Sabina, the hint was that we need an appropriate half reaction. Why? Why do we need an appropriate half reaction? Yeah, we want moles of electrons, but we're going to start out that little calculation with what? From the question. They didn't give us moles of electrons. They gave us what? Grams of silver. So that little n is technically 45 grams of silver. It's just the wrong unit. It's got to find what 45 grams of silver is chemically equivalent to. And if you want to convert grams of silver, or really any compound into another compound, you need a what bridge? Mole bridge. A reaction. So we need a reaction that involves silver and electrons. That's what this appropriate half reaction thing is talking about. So if you look at the reaction, there's really two half reactions you can write, but you really only care about one of them. Danny, which half reaction are we really going to be interested in? Right? Can you see how you can write two half reactions here? Right? This guy goes to this guy, or this guy goes to this guy. Which one would you be interested in? Well, with the Mg, though, they didn't give us any info about it. So we would write, what on this side? Anybody help her out? What is this? You could write 2Ag plus, but I'm going to show you that you really don't need to. Ag plus goes to Ag solid. Okay. How do you balance this thing? Yeah, well, only one right now. But if you wanted to have two Ag pluses go to two Ags, you have to add 2 electrons. But regardless, the ratio is what to what? It's always 1 to 1. So if you want to write 2, fine. But the ratio is always 1 to 1 for moles of electrons to moles of silver. So there's our mole bridge. 1 mole of electron equals 1 mole of silver. Okay, so let's go ahead and see if we can work this out. Convert 45 grams of silver to moles of electrons, and we need our little mole bridge up here. What would be the first step to do this, Diana? What would you do? Of the Ag, and I can never find this stuff. What does that say? The glare's on it. So 107.9 probably. So 107.9 grams of silver and 1 mole of silver. Excuse me. Teresa, then what? Yep, 1 mole to 1 mole. 1 mole of silver to 1 mole of electrons. You know it's not always going to be 1 to 1, because there's a lot of half reactions that don't involve 1. But and then we stop there. 45 divided by 107.9. I got about 0.417 moles of electrons. So that's my little n. So we got it. My W max would be negative 0.417 moles of electrons. 96,485 coulombs per mole of electrons. I don't have much space here. And then times 1.15 volts. So I got about, so I don't have to write so much. I could just call it 46 kilojoules, right? Because didn't you get like 46,275? So I'm just going to give my answer in kilojoules, so I don't have to write so much. Make sense? Now, what about that minus sign? Am I supposed to erase it? No. When we got a minus sign for Q, for heat, did we erase it? No. If you had negative heat, what did that mean? Alyssa, what did that mean? If you had negative heat. It meant it was what type of reaction? Exothermic. Exothermic, so it was losing heat. So the system is losing energy. This is supposed to be a negative sign because the system, I don't know, think of it as a battery. The little battery is losing energy to make the little car run around. So it is. It's negative energy. It's energy that's lost from the system. So negative 46 kilojoules. Okay. or negative 46,000 joules, whatever you like better.
But that's not
Hmm?
Is that still powerful?
I think to put it in perspective, a Snickers bar you eat one Snickers, what is it, like 200 kilocalories or something? Or 200, what does it say on there?
Yeah, like 100, just 60.
Right? Doesn't it say like 200 kilocalories or something? Okay. Now, there's 4.184 joules in a calorie. So you could convert out and just convert that to a fraction of a Snickers bar if that gives you, right? So standard cell voltages, E0 cell. If a cell is made with all concentrations of 1 molar, gases are at 1 atmosphere, keep the temperature at 25 degrees Celsius. Those are the standard conditions. That's why they have a little superscript 0 on the E0 cell. We can measure all these half-cell reactions. They actually have to set them up with a standard hydrogen electrode, the guy in the box, right? Or where is it, standard hydrogen electrode? Well, set up all these, make sure all the conditions are right. 1 molar, 25 degrees Celsius, 1 atmosphere. And then all these voltages hold true. You can actually set it up in the lab and you'd measure those voltages. So what we can do is take any 2 of these, build it, and we can measure what's on the voltmeter, E0 cell. So these are all half reactions. So I think the only trick to knowing how to use this table is if you find a reaction, but it's actually flipped, like silver solid, it's on the reactant side, right? And silver plus and E minus are on that side. You just got to do what to the sign? Change it. So just make sure we know what we're doing here. So we've got the table. Gabby, what would be the E0 for this half reaction, for A? What would be the E0 for it? I think it's right here. Yeah, I think you go across, you read negative 0.25. And what are the units for it, everybody? Volts. Okay. How about B, crystal Zamora? How about B? Positive 0.25 volts, because all we did was just flip it. Now, one thing to help you out here, when you're looking for these reactions, notice the electrons are always on which side? Reactant or product? They're always on the reactant side. These are all reduction potentials. Everything's getting reduced here. Like look, cadmium plus 2 going to cadmium. Iron plus 2 going to iron. These are all reduction potentials. Okay. So if you're looking for something in here, it's all tabulated with electrons on the reactant sides. I don't know, that might help you find stuff. How about C? Danielle, how about C? What would be the volts for C? So we flipped it. So do you see? I see 2 possible answers. Do you guys? She said positive 0.25. I see that as one possible answer. Or positive 0.75 because we multiplied through by 3, right? Now only one of these can be right. Jasmine, what we need to recall are intensive properties of substances versus extensive properties of substances. And what that means is take a look at density of water. If I have a little bottle of water here, the density of the water is what? What's the density of water? 1. Anybody help her out? Units for density are almost always conventionally grams mass over volume, so grams per
Liters.
mil, grams per mil. So milliliters. So density of water is 1 gram per mil. Okay, that's just the density of pure water, 1 gram per milliliter. So now I take 1 drop of that water. What's the density of that little droplet? Same thing. So density is a intensive property. Okay, volume of water is an extensive property because it depends on the amount. Intensive doesn't. All of these voltages are intensive properties. It doesn't matter the amount. So you could multiply through by 100. It's not going to change your number. The only way to change these numbers in that table is to what? Reverse the reaction. Flip those reactions. That's the only change that you can make. Okay? So that's something to remember.
So it's 0.25.
Oh yeah, we should make that clear. Not that one. It's this one. Okay. Find the overall cell reaction and standard EMF for the Voltaic cell. So when I see something like this, immediately my thought goes to doing something like this. What am I doing there? Monica, what am I doing here? What am I setting up? What am I trying to set up? The half reactions. Add them up so what cancels, everybody? The electrons. So it didn't only want the overall cell reaction. It wanted the standard EMF for the whole darn cell. So I also have to write my E zeros over here, right? From the table. Add them up, and I'll have my answer for the E0 cell, right? This will be my answer for the E0 cell if I just add them up. So go ahead, dig out those half reactions. And remember, the trick to doing that is pretty much just replacing those horizontal lines with a arrow, right? Because it's always product going to reactant. So identify those half reactions, add them up so the electrons cancel, write down their E zeros from the table, and get E0 cell and the overall cell reaction. So if you're not sure, just ask, and I can help you out. Yeah, they have to cancel. So like on the top one, you'd probably write Ni solid, Ni plus 2. And if you're not comfortable doing the electron thing, you can just find them in here, right? But you pretty much got to find them in here anyway, because you have to write down the voltage, right? So for that one, the electrons are on the product side, so you have to flip whatever's in here. So positive 0.25 volts.
Did the volts just get added?
Yeah, you're just going to add up the volts. So that top half reaction should be looking like that with a positive 0.25 volts. And then you have Ag plus going to Ag solid.
0.8.
And that's only one electron. And Crystal says that was 0.8. Right, so then the final answer is, 1.05. Now that's the final E0 cell, but you still got to get the overall reaction. Is the 0.8 negative? So Ag plus, where is it? Where is Ag plus an electron? I can never find stuff in here. Oh, there it is. Yeah, right up here, right? Ag plus an electron gives Ag solid. Because it's written exactly the same as the table. So don't flip it. You read it right from the table. Read it right in the table, right? The other one we had to flip because the reaction is flipped. So multiply the bottom reaction through by what? What do you multiply the bottom reaction through by? 2. All right, so then my electrons will cancel. So you should end up with a nickel solid and 2 Ag plus goes to nickel plus 2 and 2 Ag solid.
Why did you multiply by 2?
Because otherwise the electrons wouldn't cancel out.
Because there's 2 on.
Yeah. And when we multiplied through by 2, we did not mess with that 0.8. It's an intensive property. Okay. You comfortable with that?
Yeah.
All right. Try this one then. Find the maximum work if 28 grams of tin is obtained, right? So someone built this cell, they masked the electrode before and after, and they got 28 grams of tin in the end. What's the maximum work they got out of that they could get out of that? I doubt if they got that much because they lose, but it's theoretical maximum. Yep, the W max. You're going to need a mole bridge. What I would do is I would write out the half reaction. And it doesn't involve lead, it involves the tin. So I'd write out this guy's half reaction. And if you're not sure how to write it, just find it in the table, right? Because it's in there. So this one is not 1-to-1. All right. And give your answer in kilojoules. Because we want the ratio of tin solid, right? Because they have 28 grams of tin solid, 2 moles of electrons. Because N has to be moles of electrons. So tin solid has a 1, but we have 2 electrons. So you have to write that half reaction, because sometimes it's 3-to-1. You're going to be way off if you don't. I don't know. 7.
Negative 25 kilojoules.
That's what Sabina got.
Which has been back.
So what did you get for N? 0.47. So I think you should get 0.47 moles of electrons, and then substitute it in to W max. I guess you should write negative joules first and then convert it later so people don't get confused.
What is the N unit?
N has to be moles of electrons. Right, so
No, I mean the last unit.
because you want to see how moles of electrons has to cancel there.
So
The last unit would end up being coulombs times volts. So you could actually write big C times big V. But no one's going to recognize what the heck you just wrote. It's not wrong. You should write joules because a coulomb times a volt is a joule.
all we do is multiply, right?
Mm-hmm. So if you got it, go on to the next one. I think negative 25 kilojoules is what you should get. Yeah. Negative 24.
So do we convert it?
Well,
Yeah. See, because I got, that's what I got.
yeah, I asked for it in kilojoules though, so. But it works. Has to be negative. So go on to the next one. If you didn't get it, let me help you out. Making sense? Okay. It's cold over here. Why don't you guys just shut it off? Keeps you awake?
Yeah.
Jeez. Man, I get sick if I stayed back there. Got oats on ya. There you go. Yeah, so multiply the top one through by, there you go. Yep. Yep. So you got an overall of 0.3 volts.
Yeah.
E cell. So did anybody else get 0.3 volts as a E0 cell for A? Did you? Sabina did. 0.3 volts. Okay. So you should be getting 0.3 volts as your E0 cell. And you're on the right track. Yep. Now don't multiply these. You didn't multiply these by 2 and 3, did you?
No, these no.
Okay, good.
This is what I don't want to.
Okay, now she got positive 0.3 volts.
Oh no, I haven't put it yet.
You should have a positive 0.74. And a negative 0.49. This should be positive. I mean, you forgot to flip it, I bet.
Yeah, probably.
You should have a positive 0.74.
The second one I got 0 voltage.
It adds up to 0? No way.
This one was negative, and this one was positive.
Really?
Right here.
But that's 0.31.
This one gets switched for PD.
Yeah.
It's 0.13 and it got switched to positive 0.13.
Okay. But that says 0.31 though.
Where is it? S and looking at it.
Oh, you're talking about up here?
SN, yeah, it's positive.
Oh, huh. Alrighty. Well, have a good weekend.